Okay, welcome to the NUPOC Video Study Guide number 76. I know we had a little bit of a break there of a few weeks, but I've taken care of some other things, so now we're right back to making some of these videos. So I know in number 75 we went over some problem about magnetic fields and kind of some advanced electrical engineering, and looking at the acceleration of charged particles moving through static magnetic fields and things. And one of the comments on that video was, it might be a little bit much for some of the, or for a lot of the candidates going to their NUPOC interviews, and that maybe something more appropriate would just be talking about some of these basic electrical circuit problems, especially for some of the mechanical and nuclear engineers and other engineers besides electrical. But as a caveat to that, I will say that understanding things like the Lorentz force and how charged particles interact with both electric and magnetic fields, especially in motors, both AC and DC motors, is definitely something important for the electrical engineers especially. So I wouldn't disregard video number 75 at all. It's just that something like this would also be helpful, especially for some of the non-EEs out there. Alright, so this is actually question 3 in the electrical engineering section of the second Navy study guide. And what it's asking is for you to look at these two circuits, so circuit A and circuit B, and kind of decide which one uses more power, and then also discuss the advantages and disadvantages of each. And what they've done is they've defined this symbol, this resistor with a circle around it, right? This little squiggly thing is a resistor, as a 100-watt bulb, okay? So in circuit A, all of these bulbs are wired in series. And what we're going to do is we're going to make a little bit of an assumption here when we go ahead and solve this problem. And that is, we're going to assume that in both of these circuits, excuse me, this is a 100-watt bulb in both of these circuits, right? So I believe in the solution to this, or in the solution to a similar problem, what they've done is they've assumed that it's a 100-watt bulb in this case, right? Where we would have, so this is 100 watts, this is 100 watts, and this is 100 watts, and we know there's 10 volts across each bulb, right, because there's 10 volts here, right, 10 DC volts, it's like a battery or something. So with 10 volts across this, we know, right, from power equals voltage times current, we know that the current through each of these bulbs, in this case, is the power over the voltage, so 100 watts divided by the voltage, which is 10 volts, so the current is 10 amps, right? And so that makes sense because now 10 amps times 10 volts, right, that's 100 watts, which is what we want. So here's 10 amps, and going down this wire is 10 amps. And going down this wire is 10 amps. And what they do in the solution is then they say, okay, well that means that this bulb is 1 ohm, because we know that V, voltage, equals current, I, times resistance, R. So now that we know voltage and current, we can say that R equals, right, voltage divided by current, or 10 volts over 10 amps equals 1 ohm. Right? So what they do in the solution is they go ahead and say, okay, well this is 1 ohm, so let's go ahead and call this 1 ohm in this circuit as well. So all these are 1 ohms, and when we connect them in series, it's 3 ohms, and they go from there. And if you do that, what you end up with is this current here, right, would be 10 volts over 3 ohms, right? Just using this relationship again. And so it ends up being something like 3 1/3 amps. And so when we do the when we find the total power that's supplied by this source, which is just the source voltage, times this source current, which is 3 1/3 amps because it runs through everything here, we get something like 33 1/3 watts, right? So obviously, by the solutions logic, this circuit uses more power, these bulbs will be dimmer, but hold on a minute here. For me, that doesn't seem like the correct assumption, so we're going to do it a slightly different way. That means that each of these bulbs is something like 11 watts or something like that, but we defined this as a 100 watt bulb. So in fact, I think a better way to go about this is say, in this circuit as well, this bulb is 100 watts, this bulb is 100 watts, this bulb is 100 watts, and it'll be like a slightly different bulb. It'll be have a slightly different resistance than this bulb. So maybe it's like a different style bulb or something like that, or a different type of bulb, or a different serial number or model. Different model, that's the word I'm looking for. It's a different model of bulb or something, right? That has 100 watts when you connect 3 of them in series or something like that, right? So when we assume that, if this is defined as a 100 watt bulb, and we have 3 of them in each circuit, then the answer to the first part of this question is both circuits use 300 watts. So it's almost like a trick question, right? Because they've gone ahead and defined this symbol as 100 watts. So it's going to have a different resistance in both cases, right? It's not the same bulb, but it will be 100 watts in both cases. So neither of them uses more power. They both use 300 watts. Now, let's talk about the advantages and disadvantages of each. And by the way, if you wanted to do the circuit analysis here and do something like Kirchhoff's voltage law around this loop just to work it out what the resistance would be here, excuse me, we would have 10 over 3 volts across each, with this polarity, across each bulb. And when you do the math out with these equations here, you come out with the resistance for each bulb, in this case, is only 1/9 of an ohm. 1/9 of an ohm. Whereas over here, the resistance was 1 ohm in this case. And those resistances with these DC voltage sources will give you 100 watts per bulb. Okay, sorry about that. My camera just ran out of memory suddenly, so I had to split this video into 2 parts, but we're right back where we left off. Let's talk about the advantages and disadvantages of each of these circuits here. If we have each of these as a 100 watt light bulb. So if we look at circuit A, where we have all of the light bulbs wired in series, we can say that one advantage is that if a single light bulb fails short, right? If it fails short as in if, for example, we connect a wire across, like if there's a piece of wire or something, some stray bit of metal or something, and it falls on this wire here and it shorts, as in it creates a circuit that bypasses this light bulb, we won't short the entire source. And of course, if we short the entire source, for example, if I put a wire from here to here, and there's very little resistance in that wire, then a large current will flow, it will generate a lot of heat, and it'll probably blow out the source, right? The source will just destroy itself because it'll try to source so much current, it'll heat up, and if it's a battery, it may, split open or something like that. So that's what a short circuit is, right? And in a typical power system, we would have circuit breakers that would try to create an open circuit, so break the circuit, right? That's why they call it a circuit breaker. Generally when a short circuit happens, but the great thing about wiring in series, definitely an advantage, is a single short right? A short circuit around one single bulb doesn't short the source, right? Now, this circuit has a lot of disadvantages, though. Number one, fluctuations in the power or the resistance of one light bulb, right, affects the power in the other two. And the reason for that is, right now, if they're all equal resistance, then they have equal voltage. This voltage divides equally across all three of them by Kirchhoff's voltage law, which you may want to look up. But if this, for example, had a slightly higher impedance, right, then there would be more voltage drop across it, right? And so there would be a higher, for example, if this was 2 ohms and this was 1 ohm and this was 1 ohm or something like that, the total is 4 ohms, right? But most of the voltage drop will come across this 2 ohm resistor, right? And you can use these two equations to see that. So this one might be a little bit brighter and these might be a little bit dimmer, and if I change the power here, it's going to change the voltage seen across these resistors, and it's going to change how bright they are, right? So bulb powers, I guess, interact with each other is a good way to put it. Another disadvantage is that a single open circuit shuts off the whole system. And of course, if these really are like incandescent light bulbs, they're much more likely to fail open than fail short. So if the circuit gets broken, there's no current flow, and all the lights go out. So one goes out, they all go out, kind of thing, right? Like the old-fashioned series-connected Christmas lights. So single open, and they all go out. Another one is that, another disadvantage is if these are all 100 watts like we were talking about, then there's 30 amps flowing around this whole circuit, right? Because it has to source 300 watts, and so we need to have 30 amps coming out of a 10 volt source, so that 10 volts times 30 amps is 300 watts to source this whole load here. So there's higher current throughout the whole system, so there's higher current overall, so that means more copper, right, or more conductor, which means more cost, right? If we look at this one, circuit B, the advantages and the disadvantages, they're almost like the inverse, right? So the advantages are we have fewer areas of high current because there's 30 amps here, right, out of the source, but there's only 10 amps in each bulb. So lower current overall, so less conductor is needed, right? And we can go into the physics of that. I think if you watched one of the previous videos on the geometry of a resistor and how it affects resistivity, you'll kind of understand why this is needed, why we need to have low resistance or less copper for lower current, so there's less cost. Another advantage is that a single failure can be isolated. So whether there's a short or an open here, we can put like a circuit breaker or a circuit maker around each of these branches, right? So faults can be isolated more easily. Of course, here we can always put a circuit maker around each one so we can deal with open circuit faults, but that's a little bit too detailed. So let's just say faults can be isolated. So if one of these fails short or fails open, it doesn't affect the other two lights. And of course, the resistance in one doesn't affect the other. So if this resistance changes, this bulb may become brighter or dimmer, right? But these two will stay the same brightness because they have that same 10 volts across it, across all the lights. So bulb powers don't interact, let's say. Now the disadvantage is that a single unit, if it fails short, right? It will short the source if we don't have a circuit breaker there. So if this is just like a string of Christmas lights or something, and there's no circuit breaker at each bulb, then if I put a short circuit around this bulb, or around this bulb, or around this bulb, right, then what's going to happen is it's just going to put a direct, that's like connecting this is the 10 volt rail goes from this node to this node, see, between these two nodes, right? So anywhere that I short these two nodes, right, it's going to create a short at the source, and the source will basically destroy itself unless there's some sort of circuit breaker protection. So maybe there might be like a circuit breaker here, but then again, that's going to shut off the whole system if just one bulb fell short. So anyways, one fails short and whole system shorts. Whole system shorts. And that's it. Hopefully that was a useful little demo about some basic circuits, some basic theory, power, voltage, resistance, and current.